You think the Milky Way is the largest galaxy. For most of the 20th century, astronomers thought exactly the same thing, until they looked at Abell 2029 and quietly realized the Milky Way was roughly the cosmic equivalent of a garden shed next to a city. That city exists, and it is closer than you think. How something like this formed, and how a universe with any sense of proportion managed to contain it at all. To understand that, you have to start much smaller than you expect. I'd be grateful if you'd subscribe and softly support the video. Now let's begin. There is a problem with the way humans understand scale. When you hear 400 billion stars, your brain registers it as large. So before getting to what sits at the center of Abell 2029, it is worth rebuilding that sense of scale from the ground up, not with raw numbers, but with distances that actually land somewhere in the mind. Start with the Sun, which sits 93 million miles from Earth, and whose light travels at 300,000 kilometers per second, fast enough to circle the entire Earth 7 times in a single second, and takes 8 minutes to reach your eyes. 8 minutes for the closest star, the one whose warmth you feel on a summer afternoon. If the Sun disappeared at this exact moment, you would not know for 8 minutes, because the information encoded in light has not yet arrived. Move outward. The nearest star beyond our Sun is Proxima Centauri, sitting 4.2 light-years away, which means the light arriving from it tonight left that star 4 years and 2 months ago, and has been crossing empty space ever since at 300,000 kilometers per second, arriving only at this moment after more than 4 years of uninterrupted travel. That is the distance to the nearest neighbor, 1 star. 4 years of travel at the maximum speed the universe allows. The Milky Way contains somewhere between 200 and 400 billion stars spread across a disk roughly 150,000 light-years wide. If you compress the entire galaxy down to the size of the continental United States, our entire solar system, the Sun, all 8 planets, everything out to the edge of the Oort cloud would be a single grain of sand, somewhere in the middle of Kansas, surrounded by a continent of other grains, most of them separated from each other by distances proportionally equivalent to hundreds of kilometers of empty space. The visible disk alone spans 150,000 years of light travel, and the dark matter halo surrounding it extends 1 to 2 million light-years in every direction, 10 times larger than what any photograph can capture. There are structures within the Milky Way whose size alone would seem impossible if encountered without context. The Tarantula Nebula, a star-forming region in the Large Magellanic Cloud, just neighboring our galaxy, spans approximately 1,000 light-years across and contains several million solar masses of gas in the process of collapsing into new stars. The largest known star, Scuti, has a radius approximately 1,700 times that of the Sun, meaning that if it replaced the Sun at the center of our solar system, its surface would extend past the orbit of Jupiter. And yet Scuti is a single star in a galaxy of 400 billion in a universe of 2 trillion galaxies, each containing their own populations of objects equally extreme. The scale multiplies beyond anything the brain evolved to process at every level in every direction. Step back further to Andromeda, the nearest large galaxy sitting 2.5 million light-years away, whose light arriving tonight left that galaxy when the most sophisticated technology on Earth was a sharpened stone, and the creatures using it had not yet fully learned to walk upright. 2.5 million years in transit, crossing the void between 2 island universes, arriving at a rocky planet that did not yet have anything capable of wondering where it came from. Together, the Milky Way, Andromeda, and roughly 50 smaller satellite galaxies form what astronomers call the Local Group, a gravitationally bound collection spanning approximately 9.8 million light-years from edge to edge, containing dozens of galaxies and hundreds of billions of stars, which is by cosmic standards a quiet backwater, a small neighborhood in an incomprehensibly large city. Beyond the Local Group sits the Virgo supercluster, a structure containing more than 100 galaxy groups and clusters spanning approximately 520 million light-years across, within which the Local Group itself occupies a modest corner known as the Virgo subcluster. And beyond that, The Laniakea supercluster discovered and named in 2014 spans 500 million light-years and contains the mass of 100 million billion suns, with the Milky Way sitting near its outer edge, one small galaxy in a structure so vast that its name comes from the Hawaiian word for immeasurable heaven. Astronomers identified Laniakea by mapping the gravitational flows of galaxies across enormous volumes of space, finding that hundreds of thousands of galaxies are all slowly drifting toward a common point called the Great Attractor. That drift defined a structure which had existed for billions of years without anyone recognizing it as a single thing, and the numbers start to blur. That is exactly the problem, because what sits at the center of Abell 2029 is not 2 times larger than the local group, not 10 times larger, but large, in a way that makes all the previous numbers feel as though they were not even playing in the 29. Same game. IC 1101, a single galaxy containing 100 trillion stars, 250 times the stellar count of the Milky Way, with a diameter somewhere between 4 and 6 million light-years, depending on where you draw the boundary of its outermost halo, which fades gradually into surrounding space, rather than ending cleanly. Even at the conservative end of that range, it is roughly 40 times wider than the Milky Way. At the full extent of its diffuse outer envelope, it approaches 40 times the diameter of the entire local group, the whole neighborhood, all 50 galaxies contained within a single structure. If IC 1101 replaced the Milky Way at this moment, it would not simply absorb our galaxy. It would extend past Andromeda 2.5 million light-years away. It would swallow the Triangulum galaxy, the Large and Small Magellanic Clouds, every member of the local group, all of them contained within the boundaries of one galaxy with room remaining. The diameter of IC 1101 is approximately 1/18 the diameter of the entire observable universe, one galaxy out of 2 trillion, occupying a span equivalent to a continent on a planet the size of Earth. The measurements were checked multiple times when astronomers first produced them, not because the instruments were faulty, but because nothing in prior experience had prepared anyone for something this extreme. A galaxy this large should not intuitively be possible. And yet every time the numbers were checked, the answer came back the same. IC 1101 is classified as a supergiant elliptical galaxy, specifically a type called a CD galaxy. The designation standing for central dominant, meaning it sits at the gravitational center of its cluster and has grown by consuming surrounding material over billions of years. CD galaxies are always found at the centers of rich galaxy clusters, always old, always elliptical, always surrounded by extended halos of diffuse light from stars stripped from smaller galaxies during mergers. They are the universe's most extreme products of long-term gravitational accumulation, and IC 1101 is the most extreme example of an already extreme category. Its central surface brightness is so high that it was first catalogued by astronomers in 1964, years before the full extent of its outer halo was appreciated, because the instruments of the time were not sensitive enough to detect how far that halo actually extended. When more sensitive observations revealed the full picture, the galaxy turned out to be significantly larger than the initial measurements had suggested. Consider what this means for the numbers that came before. The Sun seemed large relative to Earth. Proxima Centauri seemed impossibly far at 4 light-years. The Milky Way, at 150,000 light-years wide, seemed like the upper limit of what the universe had to offer. Each step felt enormous, and each one turned out to be a small increment on a scale that keeps going long after intuition has given up entirely. The universe does not care about human intuition. It does not scale its structures to what our brains can comfortably process. It builds what the laws of physics allow over the time available, using whatever matter and gravity have to work with. And given 13.8 billion years and the right conditions, it apparently builds IC 1101. Which immediately raises the question that scale alone cannot answer. Something this large did not simply appear. No structure in the universe assembles itself from scratch, and the process by which IC 1101 was built turns out to be one of the most quietly relentless stories in the history of the cosmos. Nothing in the universe is born large. Every massive structure that exists, every giant star, every sprawling nebula, every galaxy cluster, spanning hundreds of millions of light years, started smaller and grew by pulling things in. The universe does not manufacture size, it accumulates it. And for galaxies, the mechanism of accumulation has a name that is almost refreshingly honest about what is actually happening: galactic cannibalism. The basic physics works like this. Two galaxies drift into each other's gravitational field, and at first, nothing dramatic happens because they are too far apart for any individual components to interact directly. But gravity is patient, and over hundreds of millions of years, the two structures begin to distort each other, their spiral arms stretching and warping, their stars pulled sideways out of orderly circular orbits. The galaxies make one slow pass through each other, then swing back around for another, losing energy to gravitational friction with each pass, until eventually neither can escape the other's pull. The thing that surprises most people is what does not happen during this process. Even when two galaxies are actively merging, passing through each other with their structures dissolving and their stars scrambling into new orbits, the individual stars almost never actually collide. The distances between stars are simply too vast. If you scaled the Milky Way down so that each star was the size of a marble, the nearest marble to yours would be approximately 300 kilometers away, which means two galaxies can pass through each other like two swarms of bees, moving in opposite directions, and the individual bees almost never touch. What changes is everything else: the gas, the dust, the gravitational potential of the combined system, and eventually the shape of both structures entirely. The gas clouds in each galaxy compress as they meet, triggering enormous bursts of star formation. Thousands of new stars per year, sometimes tens of thousands, compared to the Milky Way's relatively quiet rate of 2 or 3 per year. The ordered rotation of two spiral disks, the sweeping arms and flat geometry that make galaxies look beautiful in photographs, dissolves into a single chaotic structure. What is left after the merger settles is an elliptical galaxy, smooth, featureless, roughly egg-shaped, dominated by old stars moving in randomly oriented orbits, looking ancient and quiet, like something that has forgotten what it once was. One of the most striking features of galactic mergers is what they do to the timekeeping of stellar populations. A spiral galaxy before a merger contains stars of many different ages, with ongoing star formation continuously adding younger populations to older ones. After a major merger, the starburst triggered by the collision produces an enormous cohort of stars, all born at roughly the same time, what astronomers call a coeval population. These stars then age together, burn through their fuel at rates determined by their initial mass, and eventually die together, leaving behind a galaxy whose stellar population carries a timestamp embedded in its chemistry and color. By analyzing the light from an elliptical galaxy and measuring the ages and compositions of its stellar populations, astronomers can reconstruct a rough merger history, even billions of years after the fact, the way a geologist reads the history of a cliff face in the layering of its rock. IC1101's stellar populations tell a story of repeated starburst events separated by long, quiet periods, each burst corresponding to a major merger. Each quiet period, the aftermath of the black hole's thermostat, bringing things back under control. IC1101 has gone through this process at least 10 times, possibly significantly more. The evidence is written in the unusual smoothness of its outer halo, the diffuse cloud of stars extending 4 million light-years from the galaxy's center. Each merger leaves gravitational scars, streams of stars in unusual orbits, distortions in the distribution of stellar populations, subtle asymmetries in the overall structure. IC1101's halo is remarkably smooth, which tells astronomers that it formed early in the history of the cluster, and has had billions of years to settle, time enough for each scar to fade and each piece of evidence to be slowly erased by the relentless averaging of gravity over cosmic timescales. The galaxy has been eating for so long that it has stopped showing its work. Every one of IC1101's 100 trillion stars arrived from somewhere else, Many came from galaxies that no longer exist as independent structures pulled in over billions of years with their stars stripped loose by tidal forces and scattered into IC1101's growing mass. If you could trace each star back through time to its origin, you would find hundreds of different birthplaces, hundreds of former galaxies, each one now dissolved and absorbed, contributing its stellar population to the largest structure in both the observable universe. Tidal stripping, the process by which a larger galaxy pulls stars off a smaller one before fully absorbing it, is particularly efficient in dense cluster environments like Abell 2029. A small galaxy falling toward IC1101 does not survive intact. The gravitational gradient between the near side of the infalling galaxy and the far side is strong enough to pull stars off its outer regions long before the core reaches the center of IC1101. These stripped stars form tidal streams, long arcing trails of stars following the orbital path of the galaxy that used to contain them. And over billions of years, these streams dissolve into the general stellar population of the larger galaxy's halo, the diffuse outer halo of IC1101. The part that makes it so enormous is in large part a symmetry of tidal streams, the dissolved remains of galaxies that wandered too close and were taken apart piece by piece before disappearing entirely. Galactic cannibalism is not an exotic process at the extreme edge of what the universe does. Approximately 25% of all galaxies observable today are currently in some stage of merger, 1 in 4 actively in the process of absorbing or being absorbed. The universe has been running this process continuously for nearly 14 billion years, and its cumulative output is the population of enormous elliptical galaxies sitting at the centers of the largest clusters, each one a graveyard of hundreds of smaller structures that no longer exist independently. The Milky Way is part of this story. Our galaxy is absorbing the Sagittarius dwarf galaxy, a small satellite that wandered too close and is being pulled apart by tidal forces, its stars stretching into long streams that wrap around the Milky Way like the remnants of something that used to be whole. The large and small Magellanic clouds, visible from the southern hemisphere as faint smudges of light, are gravitationally bound to the Milky Way and will eventually be drawn in. In approximately 4.5 billion years, the Milky Way and Andromeda will collide in a merger lasting billions of years, eventually producing a single large elliptical galaxy that will look in some fundamental ways like a smaller version of what IC1101 already is. In June of 2024, data from the European Space Agency's Gaia Space Telescope revealed that the Milky Way completed a significant merger far more recently than previously estimated. The evidence came in the form of subtle ripples in the distribution of stars throughout the galactic disk, the kind of disturbance that forms when a large object has recently passed through and disturbed the existing structure, universe's version of footprints left in sand. Our galaxy is still settling from its last major meal. Astronomers have identified the likely culprit as a dwarf galaxy called the Kraken, a structure containing several hundred million stars that merged with the Milky Way approximately 11 billion years ago, before the galaxy had developed. Its characteristic spiral structure, the Kraken merger, is thought to have been the most significant event in the Milky Way's entire history, a collision that fundamentally reshaped the proto-galaxy and contributed a substantial fraction of the mass now concentrated in its central bulge. The Milky Way you see today, its spiral arms, its central bar, its population of old stars in the bulge, was partly shaped by an event that ended 11 billion years ago, whose evidence survived in the distribution of stars long enough to be detected by a telescope launched in 2013. IC1101 is the most extreme product of this process that has ever been found. 100 trillion stars, accumulated over 13 billion years of mergers and absorptions, in a galaxy that has grown so massive, it now constitutes one of the dominant gravitational anchors of its entire cluster. But here is what is genuinely strange about it. Despite that accumulation, despite containing more stellar raw material than almost any other structure in the observable universe, IC1101 is not forming many new stars. It is quiet. It is dark. Its light is dominated by old, reddish, slowly burning stars that have been burning for billions of years, and something sitting at its center is holding the whole process in check, regulating it with a precision that took astronomers decades to begin understanding. Everything known about IC 1101, its size, its merger history, its 100 trillion stars, comes from a single source light that left that galaxy approximately 1 billion years ago and has been crossing empty space ever since, arriving at Earth only recently. This is not a minor technical detail. It changes what it means to observe something at cosmic distances in a way that is worth sitting with for a moment. Light travels at 300,000 kilometers per second, which is the fastest anything in the universe can move. Not just the fastest technology currently available, but the absolute physical speed limit imposed by the laws of nature themselves. And even at that speed, crossing 1 billion light-years takes 1 billion years. The light arriving from IC 1101 is not a current image. It is a fossil, a record of what that galaxy looked like before complex animals existed on Earth, before the Cambrian explosion, before anything with eyes or a nervous system had ever lived on this planet. When you look at IC 1101 through a telescope, you are not seeing it as it is. You are seeing it as it was 1 billion years ago. IC 1101. As it exists in this moment, its current number of stars, whether additional mergers have occurred in the intervening billion years, what has happened to its central black hole, how its structure has evolved, is completely unknowable. That information is encoded in light that left IC 1101 a billion years ago and will not arrive for another billion years. In the most literal physical sense, every observation of it is an observation of the past. This is true of everything in the sky, at every distance. The sun you see is 8 minutes old. The Andromeda galaxy you see is 2.5 million years old. The most distant galaxies, observed by the James Webb Space Telescope, are over 13 billion years old images of structures that formed when the universe was less than a billion years old, which may look completely different today, or may no longer exist in any recognizable form. Every object in the night sky occupies a different position in time, and all of them arrive simultaneously at the same pair of eyes. The sky is not a snapshot of the universe as it currently exists. It is a layered archive in which each distance corresponds to a different moment in cosmic history. There is no such thing as a shared present across cosmic distances. This is not a philosophical abstraction. It is a consequence of special relativity, the framework Einstein published in 1905, which demonstrated that the concept of simultaneity is not absolute but depends on the relative motion and position of the observers involved. Two observers separated by millions of light years cannot agree on what is happening at any given moment because the concept of that moment does not have a consistent meaning at those scales. By the time light from one location reaches another, time has moved on, and the universe that sent the signal is already different from the universe that receives it. The implications go further than simply not knowing what a distant galaxy looks like right now. They mean that when astronomers talk about the observable universe, they are describing not a place, but a time-smeared volume, a region of space in which every point corresponds to a different moment in history. The edge of the observable universe, the cosmic microwave background radiation detectable in every direction, is not the physical boundary of space, but the earliest moment from which light has had time to reach us, approximately 380,000 years after the Big Bang, when the universe cooled enough for hydrogen atoms to form and light to travel freely for the first time. What we observe at that boundary is not the universe at its edge. It is the universe at its beginning. What makes IC 1101 particularly striking in this context is the specific gap involved. 1 billion years. When the light arriving tonight left that galaxy, the Earth it was aimed at did not yet contain any animal life. The Cambrian explosion, the event that produced the first complex multicellular animals, occurred approximately 540 million years ago. When the light from IC 1101 departed, even that was still 460 million years in the future. The planet the light was traveling toward was covered in shallow seas, populated by single-celled organisms with nothing present that could be described as seeing or experiencing or wondering about anything. What the Earth did have 1 billion years ago is worth understanding in some detail because it makes the light's journey more concrete. The supercontinent Rodinia was in the process of beginning to break apart a geological event that would reshape the planet's surface over the following hundreds of millions of years. The atmosphere was gaining oxygen at an accelerating rate through the photosynthetic activity of cyanobacteria, a process that had been running for approximately 2 billion years by that point and had already transformed the early Earth from an oxygen-free environment into one capable of eventually supporting complex aerobic life. Simple multicellular organisms existed in the ocean's colonies of cells that had learned to cooperate but had not yet developed the specialized tissues, organs, or body plans that would appear in the Cambrian. The average temperature of the planet was significantly higher than today. The day was shorter, approximately 18 to 19 hours, because the Earth was rotating faster and had not yet been slowed to its current rate by billions of years of tidal friction from the Moon. For 1 billion years, the light from IC 1101 crossed empty space, passing through regions so vast and so empty that it went enormous stretches without interacting with a single particle. It arrived at a solar system that did not exist when it departed. It reached a planet that had formed, cooled, developed microbial life, developed complex multicellular life, produced vertebrates, produced mammals, produced primates, produced a species that developed language and mathematics and telescopes, all in the time it took that light to make the crossing. And from that light, 1 billion years old, carrying information about a galaxy as it existed before animals existed on Earth, astronomers extracted the mass of IC 1101's central black hole, the total count of its stars, the massive extent of its dark matter halo, and the history of at least 10 major mergers. Not from visiting it, not from sending anything there, from catching the light that happened to be traveling in their direction and reading what it contained. The technique involved is called spectroscopy, the analysis of light broken into its component wavelengths by a prism or diffraction grating, revealing the chemical fingerprint of whatever produced it. Every element absorbs and emits light at specific wavelengths determined by quantum mechanics, and those wavelengths are constant throughout the universe. A hydrogen atom in IC 1101 absorbs and emits light at exactly the same wavelengths as a hydrogen atom in a laboratory on Earth. Which means that by analyzing the spectrum of light from a distant galaxy, astronomers can determine what elements are present in it, how hot its stars are, how fast it is rotating, and because the expansion of the universe stretches those wavelengths toward the red end of the spectrum in a predictable way, how far away it is. 1 billion years of travel read in the shifting of spectral lines. The IC 1101 that exists in this moment is unknown and unknowable. In the billion years since the light we observe left that galaxy, anything could have happened. Additional mergers, shifts in the activity of the central black hole, changes in the stellar population as older stars exhaust their fuel and die. The IC 1101, visible through any telescope, is a 1 billion-year-old photograph of something that has continued evolving ever since, and the actual current state of that galaxy is encoded in light that is still a billion years away from arriving. The universe does not offer real-time observation. It offers archaeology, the past delivered at the speed of light, arriving precisely when it arrives, and not a moment sooner. And yet there is something holding IC 1101 together that the light itself cannot show directly, something that accounts for the majority of the galaxy's mass that existed before any of its stars were born, and that will still be there long after the last one goes dark. Everything visible about IC 1101, every star, every cloud of gas, every piece of matter that interacts with light in any way, represents roughly 10 to 15% of the galaxy's total mass. The remaining 85 to 90% is something that has never been directly observed, cannot be photographed, cannot be detected by any instrument that measures light of any wavelength, and passes through ordinary matter without leaving any trace. Tens of billions of particles of this substance are moving through your body every second, passing through walls, through floors, through the planet beneath you, and out the other side. without interacting with a single atom of ordinary matter. No experiment you could run in any laboratory in the world would tell you they were there. And yet, they make up roughly 27% of everything that exists in the universe, compared to the 5% that makes up stars, planets, gas clouds, and everything humans have ever directly observed or touched. Astronomers call it dark matter, and the reason they know it exists has nothing to do with detecting it directly. It has everything to do with what would happen if it were not there. In the 1970s, astronomer Vera Rubin was studying the rotation of spiral galaxies, measuring how fast stars at different distances from the galactic center were orbiting. Physics predicted a clear result: stars close to the center, where most of the visible mass is concentrated, should orbit quickly, and stars in the outer regions should orbit more slowly. The same principle that makes Neptune orbit the Sun in 165 years, while Mercury completes its orbit in just 88 days. The outer planets move slowly because they are far from the gravitational source. What Rubin found was that the outer stars were not slowing down. Stars at the very edge of a galaxy were orbiting at roughly the same speed as stars near the center, regardless of how far out they were, which under any known model of physics means the galaxy should fly apart. The visible mass, all those billions of stars, does not provide nearly enough gravitational pull to hold the outer stars in their orbits at those speeds. Something else, something massive, something not visible to any telescope, had to be providing additional gravity throughout the entire galaxy, including in regions that looked completely empty. Rubin's findings were not immediately accepted. The idea that most of the universe's mass consisted of something that had never been detected, something that interacted with ordinary matter only through gravity, contradicted the intuition of many physicists who believed that a force as significant as dark matter would have left some detectable signature beyond its gravitational effects. It took roughly a decade and confirmation from multiple independent lines of evidence before the scientific consensus shifted. The gravitational lensing of distant galaxies, the behavior of galaxy clusters in collisions, the acoustic oscillations preserved in the cosmic microwave background, all of them independently pointed to the same conclusion. There is more matter in the universe than can be seen, and it is distributed in a way that precisely matches the predictions of dark matter models. That something is dark matter, and it does not just fill galaxies. It surrounds them in enormous spherical halos, extending far beyond anything that can be photographed. The Milky Way sits inside a dark matter halo estimated at 1 to 2 million light-years across, between 7 and 14 times larger than the visible disk. And without that halo, the outer stars of the Milky Way would be moving too fast to remain in orbit, and the galaxy would slowly come apart. The galaxy cluster Abell 2029, where IC 1101 is located, contains thousands of galaxies, vast clouds of superheated gas, and a quantity of dark matter equivalent to more than 100 trillion solar in mass. Observations from NASA's Chandra X-ray Observatory confirm that 70 to 90% of the total mass of the cluster is dark matter, which means the galaxies inside it, including IC 1101, with all its 100 trillion stars, are not the dominant component of the cluster. They are embedded in an invisible structure of far greater mass, held in place by the gravity of something that cannot be seen. The Bullet cluster, located about 3.7 billion light-years from Earth, became one of the most important pieces of evidence for dark matter in the early 21st century. The Bullet cluster is actually two galaxy clusters that collided approximately 150 million years ago, passing through each other and leaving behind a distinctive separation between visible matter and mass. When the clusters collided, the hot gas in each one, which makes up most of the visible mass of a galaxy cluster, slowed down due to electromagnetic interactions and became concentrated in the region between the two clusters. But the dark matter in each cluster, interacting only gravitationally, passed straight through the collision without slowing, remaining concentrated around each cluster's original core. Gravitational lensing maps of the Bullet cluster showed two large concentrations of mass sitting well separated from the visible gas, in positions that only make sense if most of the cluster's mass was in something that did not interact with itself or with ordinary matter during the collision. The bullet cluster is essentially a photograph of dark matter caught in the act of behaving differently from everything else. In January of 2026, NASA released results from a new analysis using data from the James Webb Space Telescope, the most detailed map of dark matter ever produced. The map covers a region of sky approximately 2.5 times the size of the full moon, contains the gravitational signatures of nearly 800,000 galaxies, and is twice as sharp as any previous dark matter map. What it reveals with a clarity that earlier instruments could only suggest is a cosmic web-dense concentrations of dark matter, connected by thin filaments stretching across hundreds of millions of light-years, an invisible skeleton on which everything visible in the universe is arranged. The web structure in the January 2026 map confirms predictions made by computer simulations of the early universe that have been running since the 1990s. The simulations begin with conditions similar to those of the early universe, with slight density variations preserved in the cosmic microwave background, and allow gravity to work on dark matter over simulated billions of years. The result in simulation after simulation is the same filamentary web structure observed in real data: dense nodes where filaments intersect with galaxy clusters forming at those nodes and long threads of dark matter connecting them with galaxies arranged along the threads like beads on a wire. The match between simulation and observation is precise enough that cosmologists now use the large-scale structure of the universe as one of the primary tests of dark matter models, adjusting the properties of hypothetical dark matter particles in simulations until the predicted structure matches what telescopes actually see. Wherever the map shows a concentration of dark matter, there is a cluster of visible galaxies. Wherever it shows a filament connecting two concentrations, there is a corresponding thread of visible gas and stars. The alignment between dark matter and ordinary matter is not approximate. It is precise. Dark matter clumped first after the Big Bang, and ordinary matter fell into those clumps drawn by gravity into regions where dark matter had already gathered, slowly accumulating into gas clouds that became stars and stars that became galaxies. Ordinary matter did not lead, it followed. The same is true of IC 1101 at a scale 250 times larger than our own galaxy. The 100 trillion stars, the 6 million light-year diameter, the merger history built over 13 billion years. All of it is embedded in and supported by an invisible structure of dark matter that constitutes the true majority of billion, the galaxy's mass. The IC 1101 you could photograph is the surface of something whose actual extent is mostly hidden from every instrument ever built. But dark matter, for all its mass, is passive. It provides the gravitational framework within which visible matter accumulates. It does not regulate what happens inside the galaxy, does not respond to bursts of star formation or shifts in gas temperature, does not intervene when the process of accumulation threatens to run out of control. The thing that actually controls the internal dynamics of IC 1101, that determines whether stars form or do not form, that has been maintaining equilibrium inside this galaxy for billions of years, is something else entirely. Sitting at the very center, with a mass that makes everything around it look negligible. At the center of IC 1101, there is a black hole whose mass sits somewhere between 40 and 100 billion times the mass of the Sun. The Milky Way's central black hole, known as Sagittarius A star, has a mass of approximately 4 million solar masses. Andromeda's central black hole is estimated at around 110 million solar masses. These are already numbers that resist easy comprehension. A single object invisible to direct observation, containing the mass of millions of suns compressed into a region smaller than the solar system. IC 1101's central black hole outweighs the Milky Way's by a factor of approximately 25,000. If Sagittarius A star is a campfire, the object at the center of IC 1101 is a supernova. They share a category name and almost nothing else. In April of 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole, the supermassive black hole at the center of Messier 87, a large elliptical galaxy approximately 54 million light-years away. The image showed a bright ring of light surrounding a central dark region, the shadow of the event horizon against the glowing accretion disk. The black hole at the center of Messier 87 has a mass of approximately 6.5 billion solar masses, making it one of the largest black holes directly imaged. The IC1101 black hole is estimated at between 6 and 15 times more massive than that in a category so extreme that even the language used to describe extreme objects starts to feel inadequate. The core region surrounding this black hole spans approximately 13,700 light-years across, which makes it the largest galactic core ever measured. The distance from Earth to the center of the Milky Way is roughly 26,000 light-years, so IC1101's core alone is more than half that distance. It is not a point at the center of a galaxy. It is a structure, a region of extraordinary density that anchors everything around it across millions of light-years. A black hole's event horizon, the boundary within which nothing can escape, including light scales with mass. The event horizon of Sagittarius A star spans approximately 24 million kilometers, roughly 17 times the diameter of the Sun. The event horizon of IC1101's black hole, at the lower end of its estimated mass range, spans approximately 118 billion kilometers, approximately 12 times the diameter of Neptune's orbit. At the upper end of the estimate, it spans closer to 300 billion kilometers. The entire solar system, every planet, every asteroid, every comet in the Oort cloud could fit comfortably within the event horizon of IC1101's central black hole with room to spare. For a long time, the intuitive model of a supermassive black hole was essentially a drain matter, falls in, gets consumed, the black hole grows, end of story. What decades of observation have revealed is something far more consequential. Supermassive black holes at the centers of large galaxies do not just consume, they regulate. When gas cools and begins falling toward the center of a galaxy, it eventually forms an accretion disk, a flat, rapidly spinning ring of superheated matter orbiting the black hole at extraordinary speeds. As this material spirals inward, it releases enormous amounts of energy, some of which gets channeled into jets, focused beams of plasma and radiation, launching outward from the black hole's poles at close to the speed of light, extending hundreds of thousands or even millions of light-years into surrounding space. Those jets heat the surrounding gas, push outward against infalling material, and prevent that gas from cooling fast enough to collapse into new stars. When the feeding slows, when the gas disperses and the accretion disk loses material, the jets quiet down, the gas cools again, and the cycle begins once more. The jets produced by active galactic nuclei can carry more energy than the entire output of billions of ordinary stars. The largest jets ever observed extend for millions of light-years, depositing energy into the intergalactic medium at rates that raise the temperature of the gas surrounding the entire cluster. In some galaxy clusters, the jets from the central black hole are the dominant heat source for the intracluster gas, preventing it from cooling and falling back into the galaxy. The Perseus cluster, approximately 240 million light-years from Earth, contains a central black hole whose jets have carved enormous cavities into the hot gas of the cluster structures, visible in X-ray observations as dark bubbles surrounded by bright rims of compressed, heated gas. These cavities span tens of thousands of light-years, visible evidence of the energy being continuously pumped into the cluster by the black hole's activity. Abell 2029, where IC1101 resides, shows similar X-ray cavity structures, fingerprints of the same ongoing feedback process. The black hole acts as a thermostat for the entire galaxy. Too much cold gas accumulates, the black hole activates and heats it back up. The gas disperses, the black hole quiets, and the process of cooling and accumulation begins again. Back and forth, over billions of years, maintaining a slow equilibrium between the forces that want to create stars and the force at the center that keeps that creation in check. This is why IC1101, a galaxy with more raw material than almost any other structure in the observable universe, forms so few new stars. The 100 trillion already there represent the cumulative output of 13 billion years of this cycle, each merger briefly triggering bursts of intense star formation, before the black hole's feedback quieted things down. Again, the current state of IC1101 is the equilibrium that resulted from that process. Vast, dark, slowly cooling, held in check by the most massive black hole ever measured. In September of 2024, the James Webb Space Telescope provided the first direct observational evidence of this mechanism. Astronomers observed a galaxy called GS 10578, sometimes referred to as Pablo's Galaxy, located approximately 11.7 billion light-years away, meaning the light arrived from a time when the universe was less than 2 billion years old. What Webb detected were outflows of neutral gas being expelled from the galaxy at speeds of up to 1,000 kilometers per second, fast enough to escape the galaxy's gravitational pull entirely, with the source of those outflows being the supermassive black hole at the center actively ejecting the fuel that would otherwise have formed new stars. 1,000 kilometers per second. At that speed, the gas could cross the entire Milky Way in 150 years. It left the galaxy entirely escaping into intergalactic space, never to return, never to become stars. The black hole was not just influencing star formation, it was ending it in real time by physically removing the material needed for it. This was the first direct confirmation of a process theorized for decades, caught in action at a distance of 11.7 billion light-years. The discovery carried an additional implication that had been difficult to confirm until Webb made it possible. The galaxy being observed, Pablo's Galaxy, had already ceased forming stars at a time when the universe was less than 2 billion years old, meaning the quenching mechanism must have operated extremely early in cosmic history. In the Pablo's Galaxy, the quenching mechanism must have operated extremely early, first generations of massive galaxies. This matters because it means the feedback loop between supermassive black holes and star formation is not a late development in the universe's history, but a fundamental process that shaped the population of galaxies from very early on. The old quiet red elliptical galaxies that dominate today's galaxy clusters, including IC1101, were not passive structures that simply ran out of fuel. They were actively shut down early by black holes that grew faster than the galaxies surrounding them and have remained quiet ever since. IC1101's central black hole has been running this same process for billions of years. Every galaxy absorbed through cannibalism brought a new injection of gas and raw material. Each injection triggered a brief period of intense star formation. Each period of intense star formation fed the black hole, which heated the gas and brought the burst back under control. Creation and destruction running simultaneously, balanced against each other by a process operating on timescales of millions of years across spatial scales of millions of light years. But this balance, extraordinary as it is, will not last forever. Nothing in the universe lasts forever, and the story of how IC1101 ends, how something this large, held together by forces this powerful, eventually dissolves back into the background of a cooling universe, runs on timescales that make everything described so far look like a brief opening scene. The universe has a direction, not a direction in space, but a direction in time. And that direction, according to every physical law ever tested, points toward increasing disorder, increasing coldness, increasing emptiness. The technical term is entropy. The practical meaning is simpler: everything organized will eventually become disorganized, everything burning will eventually go dark, and everything that exists in its current form will eventually cease to exist in that form. This applies to IC1101 exactly as it applies to everything else. The second law of thermodynamics, the law that encodes this direction, states that in any closed system, entropy, the measure of disorder, never decreases over time. The universe is the largest closed system that exists, and its entropy has been increasing since the moment of the Big Bang, when all the matter and energy that would eventually become galaxies, stars, and planets was compressed into a region of extraordinary density and order. Every process since has been a step toward greater disorder: the expansion of space, the formation of stars and their eventual death, the cooling of gas and its collapse into new structures, and the slow loss of energy from every system into it, the surrounding environment. The arrow of time is the arrow of entropy, and it points in one direction only. Star formation in IC 1101 is already slow regulated by its central black hole into a quiet equilibrium. But the raw material for new stars, cold molecular gas, is finite. Over the next 1 to 100 trillion years, that reservoir will run out entirely. The last generation of stars will be born. After that, no more. The existing stars will continue burning for timescales that vary enormously by mass. The most massive stars exhaust their fuel in millions of years and end in supernovae, while the smallest, dimmest red dwarf stars can burn for 10 trillion years on a fraction of the fuel a sun-sized star consumes. But eventually every star in IC 1101 will exhaust its fuel and go cold, leaving behind white dwarfs, neutron stars, and black holes, the dense remnants of stars that once burned. White dwarfs are particularly striking objects in the context of long timescales. A white dwarf is the compressed core of a dead star, a structure roughly the size of Earth but containing a mass comparable to the Sun, supported against further collapse by the quantum mechanical pressure of electrons. A white dwarf does not burn fuel. It simply radiates its stored heat into space, cooling over billions and trillions of years. The cooling timescale for a white dwarf is so long that no white dwarf in the universe has yet had time to cool completely. Every white dwarf that exists today is still radiating, still warm enough to detect a remnant that is genuinely ancient by human standards, but still young by the standards of what the universe has time for. Eventually, on timescales of quadrillions of years, the last white dwarfs will cool to the temperature of the surrounding space, becoming black dwarfs, objects that have never yet existed in the history of the universe because not enough time has passed for any white dwarf to cool completely. Beyond that, over timescales of approximately 10 to the power of 20 years, a process called gravitational evaporation will gradually dismantle the galaxy's structure. In any large gravitational system, objects exchange energy through close encounters over time, with lower mass objects gaining enough energy to escape the system entirely, while higher mass objects sink toward the center. Given enough time, this process strips a galaxy of the vast majority of its stellar remnants, flinging them outward into intergalactic space as cold, isolated objects, white dwarfs, and neutron stars drifting alone through a universe growing emptier with every passing eon, separated from each other by distances so vast they will never interact with anything again. The universe itself is expanding, and that expansion is accelerating, driven by dark energy, the name given to the force or property of space responsible for the acceleration. In the far future, the expansion of the universe will carry all but the most gravitationally bound objects beyond each other's observable horizons. The local group, the Milky Way, Andromeda, and their satellites will eventually merge into a single structure and then become gravitationally isolated from everything else, as the expansion of space carries all other galaxies past the horizon, beyond which light can no longer reach from them. The universe will not just go dark, it will go alone. What remains at the center of IC 1101, after all of gravitational evaporation, is the black hole. 100 billion solar masses of compressed spacetime, sitting in the dark, the last significant structure remaining of what was once the largest galaxy in the observable universe. The 100 trillion stars are gone, the gas is gone, the dark matter halo remains, but without visible matter to interact with it, has nothing left to anchor. Only the black hole persists, as it has persisted for billions of years in the silence of a galaxy that has consumed everything around it and now has nothing left. And then even the black hole ends. Stephen Hawking demonstrated in the 1970s that black holes are not permanent. Through a quantum mechanical process now called Hawking radiation, black holes very slowly leak energy, emitting a faint trickle of thermal radiation from their event horizons, losing mass so imperceptibly slowly that for any black hole of significant size, the process is essentially undetectable. The mechanism involves quantum fluctuations at the event horizon, where pairs of virtual particles continuously appear and annihilate. When this happens right at the horizon, one particle can fall inward while the other escapes into space. The escaping particle carries energy that must ultimately come from the black hole itself, which loses mass by an infinitesimal amount with every such event. For any large black hole, the rate of mass loss is so slow that the radiation is far cooler than the cosmic microwave background, meaning the black hole is actually absorbing more energy from the background radiation than it is losing to. Hawking radiation, and it will continue to do so until the universe has expanded and cooled enough that the background temperature drops below the black hole's Hawking temperature. A stellar mass black hole, the kind formed when a large star collapses, would take approximately 10 to the power of 67 years to evaporate completely. For IC 1101's central black hole 100 billion solar masses, the timescale is approximately 10 to the power of 100 years. 10 to the power of 100. A 1 followed by 100 zeros. This number has a name, a Google. The current age of the universe is approximately 1.4 times 10 to the power of 10 years, which written out is 14 billion years. A Google is 10 to the 90th power, times larger than that. There is no analogy that adequately captures the difference. The ratio between the current age of the universe and the evaporation time of IC 1101's black hole is itself a number too large to be intuitive, too large to map onto any human experience, too large to do anything with, except state and move past. In the final moments of evaporation, as the remaining mass drops to the scale of elementary particles, the process accelerates dramatically. The Hawking temperature increases as mass decreases, meaning the radiation becomes hotter and more intense as the black hole shrinks. The final fraction of a second of a black hole's existence releases energy comparable to millions of hydrogen bombs in a brief burst of gamma radiation. A flash of light in an otherwise completely dark and empty universe, the last detectable event before the thermodynamic equilibrium that physicists call the heat death, from which no further change is possible, because every system has reached the same temperature and there are no remaining gradients of energy to drive any process. What is left of IC 1101 after that is essentially nothing, a diffuse scattering of dark matter, a faint distribution of photons, and fundamental particles cooling toward absolute zero in an expanding universe that is growing, darker and more empty with every passing moment. The structure that once contained 100 trillion stars assembled over 13 billion years through mergers and absorptions regulated by the most massive black hole ever measured and held together by invisible matter, accounting for 90% of its mass, will have dissolved into the background of a universe that has no further use for it. This is where the laws of physics lead not to a dramatic ending, but to a slow approach toward equilibrium, a universe at maximum entropy, cold, dark, structureless, and permanent, in which nothing happens because there is no longer any difference in energy between one place and another. Not dead exactly, because death implies something that was alive. Just finished. The way a fire is finished when the last ember goes cold. The light received from IC 1101 tonight left that galaxy approximately 1 billion years ago. At that point in Earth's history, the most complex life on this planet was single-celled organisms drifting through shallow seas. There were no animals, no plants, no eyes to see, no brains to process anything. Just chemistry slowly becoming more complicated in the dark, with no awareness of the galaxy, whose light was already traveling toward a planet that did not yet have anything capable of noticing it. That light traveled for 1 billion years, crossing the void between Abell 2029 and the Milky Way through regions so empty that it went vast stretches without interacting with a single particle, arriving at a solar system that did not exist when it departed, reaching a planet that had formed, cooled, developed microbial life, developed complex, multicellular life, produced vertebrates, produced mammals, produced primates, produced a species that built telescopes, all in the time it took that light to make the crossing. The species that built those telescopes did not know it was doing any of this for most of its existence. The anatomically modern Homo sapiens that appeared in Africa roughly 300,000 years ago spent the first 290,000 years of its existence without writing, without mathematics, without any systematic method for accumulating knowledge across generations beyond oral addition. The oldest astronomical records, preserved in physical form, marks on bones and stones that appear to track lunar cycles, date to approximately 30,000 years ago. The first observatories, structures deliberately built to track the movements of celestial objects with precision, are no more than 10,000 years old. The telescope was invented approximately 400 years ago. The understanding that the universe contains other galaxies, that the Milky Way is not the entirety of everything that exists, dates to approximately 1924, when Edwin Hubble used Cepheid variable stars to measure the distance to the Andromeda Nebula and demonstrated it was far too distant to be part of our own galaxy. The entire organized scientific study of the universe as it actually exists as a structure containing hundreds of billions of galaxies spread across billions of light years is less than 100 years old. From that light, 1 billion years old, carrying information about a galaxy as it existed before animals existed on Earth. Astronomers extracted the mass of IC 1101's central black hole, the total count of its stars, the extent of its dark matter halo, and the history of at least 10 major mergers. Not from visiting it, not from sending anything there, from catching the light that happened to be traveling in their direction and reading what it contained. From that 1 billion-year-old light, astronomers extracted the mass of IC 1101's central black hole, between 40 and 100 billion solar masses, calculated from the velocity of stars orbiting near its center. They determined the galaxy's total stellar count, 100 trillion stars, derived from measurements of its luminosity across multiple wavelengths. They mapped the extent of its merger history, at least 10 major events over 13 billion years, read from the smoothness of its outer halo and the distribution of stellar populations within it. They inferred the distribution of dark matter surrounding it, accounting for 85 to 90% of the cluster's total mass from the behavior of superheated gas visible in X-ray wavelengths. They calculated that its core spans 13,700 light-years, the largest galactic core ever measured. And they determined that its central black hole will evaporate through Hawking radiation in approximately 10 to the power of 100 years. A fact derived entirely from theory, from mathematics, developed on a planet 1 billion light years away from the object it describes. IC 1101 is 1 billion light years away, and the expansion of the universe is already carrying it further from us with every passing second. No object made of matter will ever travel there, not because of any technological limitation, but because the universe's expansion is already moving that galaxy away faster than any physical object could follow. The IC 1101 that exists in this moment is unknowable and unreachable, and the light encoding its current state will not arrive for another billion years. Carrying information about events that will already be a billion years in the past by the time that light departs. The carbon atoms in a human brain, in the neurons firing as these words are processed, were forged in stars that lived and died billions of years before the sun formed. The oxygen atoms were produced in supernovae that scattered their contents into the galaxy. The iron atoms were made in the cores of massive stars in their final moments before collapse. Every atom in every person who has ever studied IC 1101, who has pointed a telescope at Abell 2029 and extracted measurements from the light arriving there, was made in the same fundamental process that made the 100 trillion stars they were studying. The observer and the observed share an origin, separated by scale and time, and the accident of the particular arrangements of atoms that resulted in something capable of curiosity. The universe is approximately 93 billion light-years across. It contains between 1 and 2 trillion galaxies. It has been running for 13.8 billion years and will continue running for timescales so extreme that the word incomprehensible does not capture how far beyond reach they are. In the context of all of that, the emergence of anything capable of asking questions about it is statistically nearly impossible. The conditions required for a planet to develop complex life, for that life to develop language and abstract reasoning and mathematics, for that mathematics to be turned toward the measurement of distant galaxies. Each of those steps, improbable, and the chain of them together is improbable in a way that makes the word improbable feel inadequate. What makes the measurement of IC 1101 particularly striking in the full context of what has been described here is the asymmetry involved. IC1101 has been accumulating mass for 13 billion years. It contains 100 trillion stars. Its central black hole carries the mass of 100 billion suns. Its dark matter halo extends to scales that dwarf the entire local group, and it was less than 100 years old. The thing doing the measuring is by every physical metric infinitely smaller and shorter lived than the thing being measured. And yet here, the measurement exists, accurate, verified, peer-reviewed, published, and comprehensible to anyone who takes the time to read it. Every atom in a human body was forged in a star. The carbon, the oxygen, the iron in the blood, all of it produced in the nuclear furnaces of stars that lived and died billions of years before the sun formed. Scattered into the galaxy by supernovae, eventually incorporated into the nebula, that collapsed to form the solar system, eventually assembled by chemistry into structures complex enough to look back at the universe they came from and ask what it is. The universe made something out of itself that could wonder about itself. That is not a small thing, and it is not an accident that feels easy to dismiss once you understand the timescales involved. IC1101 does not know it is being observed. It does not know its history has been reconstructed from a billion-year-old signal, that the dark matter holding it together has been mapped, that the mechanism of its central black hole has been understood, that the timeline of its eventual end has been calculated. It is simply doing what the laws of physics have been doing with it for 13 billion years, slowly cooling, slowly dimming its central black hole, maintaining its ancient equilibrium, its 100 trillion stars burning through their tessent, remaining fuel at the unhurried pace of things that have billions of years yet to go. The question that opened this story, the question of what is more interesting about IC1101 than its size, ends here. Not with the scale, though the scale is extraordinary. Not with the merger history, though 13 billion years of galactic cannibalism building the largest structure in the observable universe is extraordinary. Not with the dark matter, though 90% of the universe being invisible is extraordinary. Not with the black hole that has regulated 100 trillion stars for billions of years, or the Hawking radiation that will dissolve it after a Google years, or the heat death waiting at the end of all of it. What is genuinely remarkable is that any of it is known at all. In a universe this large, running on timescales, this extreme, built mostly of matter that cannot be seen or touched or detected, the emergence of anything capable of measuring it is the most improbable thing in it. And what that thing did when it finally appeared was point its instruments at the sky, catch the light that was already on its way, and say, "We see it. We know what it is. We know how it was built, what holds it together, and where it is going." IC1101 will be gone long before the universe is finished. The 100 trillion stars will exhaust their fuel, the structure will dissolve through gravitational evaporation. The black hole will evaporate through Hawking radiation after a Google years, and nothing recognizable will remain. But the light it sent 1 billion years ago already arrived. It was caught, it was read, and from it something built from the same atoms as the galaxy it was studying looked out across 1 billion light years of space and time and understood. That is the most extraordinary thing the universe has ever done. Not building IC1101. Building something that could find it.